It's good.
Okay, sorry about that, folks. Okay, my name is David Frayer, and I'm a scientist here at Green Bank, and I'll just be going over some of the basics of the GBT. And the outline, I'll give some basic overview of the GBT. We'll touch on some of the science that GBT does. We're running a little behind schedule, so I'll probably cut some corners there. Then we'll go into the capabilities and the performance of the GBT. It's a living instrument. We've improved it. It's 20 years old now, and we've been improving it ever since it was first commissioned. And then we'll go over some basic observing strategies to give you sort of like a broad picture, and then you'll work with your individual groups later today to decide what you're going to do tonight and tomorrow. It's a 100-meter class telescope. That's very big. It's too bad you guys aren't here to get on it because it's quite impressive. If you're not afraid of heights, it's quite beautiful. And it's the largest telescope in the world that operates up the meter highest frequencies. And the unblocked aperture makes a very clean beam, as Karen was mentioning, covers a huge frequency range, it's fully movable, and as we mentioned, it's in the radio quiet zone. Following up, just give a picture what the radio quiet zone looks like. Most people that live in this area don't realize they live in the radio quiet zone. It goes all the way to Charlottesville, even. And if you go to Charlottesville, it's half of Charlottesville. I do notice if you're on the eastern half of Charlottesville, you see all those cell phone towers up on the Monticello thing. And I think that's not a coincidence. I think the western part of Charlottesville, they didn't put them there because of that. And then to the left here, I think you guys can see my cursor. I put the other mouse on so you can see the cursor. Shows the 10-mile radius just around the observatory, where we could go and complain about people's, I guess, well, we used to run a truck around and find, noisy electric blankets and stuff and such like that. The thing that makes it work at high frequency are these actuators. They're the corners of all the panels. And basically, as you move the telescope it sags due to, gravity. And we have models for that to correct for that. And then we have residual effects due to temperature across the dish that we can correct for. So we're not constantly moving these pistons during a scan, but basically at the beginning of a scan, it's set up basically and we maintain the surface of the dish to a few parts in a million in comparison to its size. Oops. And just this is an overview. If you're, whoops, I hit the button twice because my internet was slow and I didn't realize it took. This is just looking down to the right, looking down on, it's like the equivalent if you build a very big parabola and we just, built this part. We didn't have enough steel. It'd be nice to build a 208 meter, but this is sort of how it looks like. So the focus here is off to the side, and that's how you have the clean beam. In terms of pictures of it and scale, I mean, the subreflector itself is big. There's a couple of guys up here working up at the top here. So that's just a small subreflector. And then receiver cabins here. So the dish is way down below, light bounces up here and then goes into this box where we have 8 receivers. And they spin around on a turret. This is on top of that receiver room. And here, hey, if you were up on the telescope, this would be a view. But today it's actually even clearer. You don't see anything. It's very clear out there today, at least where I am. There's a 140-foot telescope there for scale. So we're looking way down on it. And here's inside the receiver room, underneath here. And that's where all the electronics are. And it's just a picture of the telescope. It moves in elevation and azimuth. And the science we cover, it's very diverse. The GBT, in comparison to, I would argue, any other telescopes, we cover a wide area of science. So we cover such a large frequency range and we touch upon a lot of different things. But there are some main areas that we concentrate on. Pulsar science, obviously, you could argue it's the world's premier pulsar telescope. And we do a lot of neutral hydrogen. Other telescopes can do neutral hydrogen as well. Our unblocked aperture really help helps getting low surface brightness and getting good dynamic range and able to detect weak neutral hydrogen emission. We do some high redshift work. I do high redshift work and some cosmology work. Chemistry, I think, well, I'm a little biased. I think chemistry might be our most exciting growth area and for the telescope. More and more groups are doing that. And it's just amazing amount of molecules you can detect in the ISM, and people are trying to understand that sort of the life cycle, how these, just physical chemical molecules can actually be made and processed actually in the interstellar medium in different environments, on grains and whatnot, and its connection to, the evolution of life, star formation and planets. Masers, we do, and star formation. So chemistry and star formation, a lot of growth area, and pulsars and neutral hydrogen at a lower frequency work. We've had a long history and it's still doing great science there. But the growth, I would say, is with the chemistry and the star formation area. That's just my personal opinion. And then, well, if we get radar system, we'll open up a completely new area of astronomy for our telescope if we get a radar transmitter. And we do 20% of our time is spent on Breakthrough Listen. They're a paid customer for the telescope. So Karen was mentioning, I think it's like 60 to 70% is open skies, and the rest of it is basically we have paying customers to use the telescope. So in terms of the layout, the Astro 2020, every decade, the astronomy community gets together and figure out what we're going to do, moving forward. And the decadal survey panel broke up these different categories, star and planet formation. So these are their categories. And we went and counted the number of white papers, papers that people wrote that that mentioned how the GBT would be helpful for us. So this is just the histogram showing the number of papers versus sort of the science area. And it just shows that we hit upon all the areas, quite a bit. Maybe regular stars, we don't. Stars are not very bright at radio wavelengths by themselves, so we haven't done a lot of stars, but we study the material from which stars form. And this is off our webpage. It's literally a screenshot of off our webpage of our Green Bank Telescope current survey. And there's web pages to these surveys. And again, we have pulsars, ammonia surveys with that's a K-band at 22 gigahertz. Well, I guess ammonia is at 23 gigahertz. Studying star formation, and then the Argus. Here's the chemistry survey, NANOGrav, which I guess you'll hear a little bit about her, is the big one trying to detect gravity waves. And then we have another pulsar survey, and here's an Argus survey for studying cores of clumps of gas that are forming stars. So when we get the radar up and going, as just sort of thing, this is a good selling point. We have a really big telescope. It would be very impressive if we had a radar system. We could be, and so down the line, we could potentially use it to, study near Earth objects. Here's just an example where the Goldstone basically was the transmitter and we were a receiver. And this is an image made radar. As I mentioned, we do consider the GBT the world's premier pulsar observatory. A lot of discoveries in pulsar science. And the main project the large project, the NANOGrav project, is trying to detect the gravity waves by looking at pulsars in different directions and the timing delays as a function of these pulsars. You can actually statistically measure a gravitational wave signal, and they're basically getting to the level at which they think they might be seeing it. So LIGO works way down on these frequencies, and NANOGrav is is down at the other frequencies. So it's in terms of the nanohertz. massive neutron stars, pulsars. And then we used to think that they were not much bigger than like 1.4 solar masses, but they're finding them up at 2 solar masses, which really constrains the equation of state of dense matter, trying to understand the physics. Just basically, they're very good clocks, pulsars are. So from that, you can measure the dynamics of systems very accurately, and you can test basic things like the equivalence principle of gravity. As I said before, it's sort of unequal sensitivity at low surface brightness, and these are just some of the projects and pictures here, seeing like within our galaxy, the Magellanic Streams, clouds around M31, the M81 group. You see that the optical galaxies are these things here, and you see the things are connected by the H1, and then there's even between M31 and M33 little clouds in between here that are very difficult to see. But they're GBT sensitive enough, they integrate long enough, integrates down nice and cleanly with good baselines, and you can go very deep. There's a large H1 survey under I can't even say it, Magna. But anyway, it's doing 2,000 low redshift galaxies, PI's Karen Masters, just some example spectrum. So these are from like the Sloan survey, a large sample of galaxies, and just literally going out and measuring H1 for them. These are the double horn profiles that you see in spiral galaxies. When they're edge on, they see both sides. And then if you look at a galaxy face on, it looks more like this because you're the velocity, there's not much velocity along the line of sight. You mentioned chemistry, and I still think this is like a big area of growth in our future in terms of using our telescope and taking advantage of our higher frequencies. And they've been studying, and we're finding more and more complex prebiotic molecules out there, very complex molecules. Here's like, this is just an example, low temperature sugar related molecule. So there's like talking about the building blocks of amino acids and stuff. So understanding sort of the chemistry cycle or the life cycle of chemistry. You got some feedback now. Okay, thank you. So here's just a diagram of like 20 some molecules. There's been about 20 plus, there's more than 20 molecules that have been found on the GBT, and here's just a picture showing some of their chemical makeups. So people study chemistry to study the length. The big picture is the link to the origin of life, but some of our astrochemists are just interested in understanding chemistry for its own sake. And then the people that work in star formation like to use chemistry as a tool to understand the physical process associated with star formation. So that's sort of different people that use astrochemistry in different ways. And in terms of studying star formation, the Herschel mission, which is an infrared mission, a space-based mission, did a lot of mapping, and they uncovered a lot of filamentary structures and stuff. So, but when you have that, it's just in continuum. So with the GBT, we've been mapping a lot of those out in ammonia, and now with Argus up at the higher frequencies. And you can basically map out the kinematics within these filamentary structures to see how they fragment and form stars. And here just, I find this picture beautiful from Rachel Friesen. She's a PI of the gas survey. It's a large GBT ammonia survey of all star forming regions over a large area of the sky. So this is like 1.5 degrees in the red here. And that's the ammonia image. There's a new survey that's undergoing. They had they did a smaller project that looked at one of the clumps, and they got very interesting results. They put in a survey, and they're going to look at about more than 100 cores in Perseus to study the kinematics of these young star forming regions. And this is, we can use not only the GBT does this, but you can combine the GBT with the VLA to go to even a higher resolution to study these cores. So GBT data is here over to the left, and then combine it with the GBT, not GBT, the GBTs, excuse me, I'm tongue-tied a little bit, mixed in with you combine the GBT data with the VLA data to push it to higher resolution and uncover basically young YSOs, or young stellar objects and outflows and the cores of these young clumps, basically. So stars are actually forming in here. In addition, the GBT is used with the VLBA and other telescopes around the world, the HSA, the High Sensitivity Array, GMVA, the Global Millimeter, VLBI work. So that we could even we combine with ALMA now every other year or something like that. And this just shows a result. There was some controversy a couple of years ago on like the size, you know, the distance of the Pleiades, because that's important in terms of the distance ladder and understanding how old the universe is, and etc. And Hipparchus was arguing results over here, and some other people have found these other results, and you see the different error bars here. But anyway, combining the GBT with the VLBA and other telescopes, Arecibo and Effelsberg, you got this and they nailed it down really well, basically, just using basically parallax. So people masers, we found a lot of masers. You can, the cool thing there, you can actually independently measure H0, but they have also can measure the masses of the supermassive black holes in the center of galaxies of a lot of objects. Just a beautiful picture, I think. This is VLB of a M87, 3C, I guess that's 3C274, if you like the 3C numbers. And that's imaging down, getting close to Schwarzschild radius, like 10 resolution of 10 Schwarzschild radius. So these are pushing higher and higher resolution. High-redshift CO, this is some of the work I've been a part of over the years. And that is also following up Herschel results. So Herschel provided a lot of targets in continuum of high redshift objects, but they didn't have redshifts. So we used the GBT to get the redshifts of the high redshift objects using 12CO, 1 to 0. These are two different objects that were detected. Yeah, here's a beautiful picture of the first one here. This SDP81. It's basically, it's been lensed by the foreground object, but so this is what it looks like in continuum, high resolution with ALMA. Studying cluster formation using our Mustang instrument. It works at 3 millimeter. It's continuum bolometer, 233 or 230 roughly bolometers, and with the GBT's resolution and sensitivity, you can actually study cluster substructure and understand the collision and cluster formation, what's going on with clusters. Clusters are very dynamic in themselves. We used to think they were just these spherical objects, but they're not. So capabilities and performances of the GBT, I'm going to go into that. And here's a list of all of our receivers. This is literally just cut out of probably the proposal guide. We cover ranges. There's some practicalities with certain, depending on what frequency you're looking at, there we have different bands within them. But anyway, we have nearly, not quite full coverage, down from 300 megahertz all the way up to 115 gigahertz. In terms of the aperture efficiency and available bandwidth, there's practice, and this is the kind of stuff where you can lean on your the observatory staff, because and when asked your questions, a lot of the stuff is documented, but if you're trying to understand exactly what can be done, feel free to ask questions from them. So we have a help desk, and if you have a project, you'll be assigned a friend, and obviously the friend will answer, or at least dig up the answer to any question you may have. And the back ends, so we have a lot of jargon, so I'm not sure people on this call, we probably have a wide range of backgrounds. So at the front ends, we call the receivers because they see the light or the radiation first, and the back ends are what we use to do the processing. We call that the back ends, and that's the spectrometers. So we have most of our work is done now with the Vegas instrument for spectral line work. We have Vegas spectral line modes, and it's Vegas stands for, I have it written down somewhere on one of the slides. Anyway, versatile basically. So you can configure it in a lot of different ways for spectral line work. We now use it for Pulsar work. We retired the previous Pulsar backend, which was called Guppy. Now, when we do pointing, so when you set up your projects, you'll configure Vegas basically for those doing spectral line work or those doing Pulsar work. When we point and focus, we use the continuum receiver, which we call the DCR, the digital continuum receiver. That's a continuum receiver. That's not. And if anybody's doing any continuum projects at the lower frequencies, we'll use that receiver. We also have a Caltech Continuum backend. It's a very sensitive, it's a fast internal electronic switching receiver, which is good for continuum work because it can remove the 1/f noise. That only works for Ka band, and Ka band is not on the telescope, so we will not be using this one. And we also are not having any VOBA projects going, but we do have a VOBA disc recorder. They go through their different versions, and I hope I'm up to date, Mark 6. I should actually talk to our VOBA expert to make sure we haven't changed that out. And then we have our radar backend as well. So here are all the modes. They're not going to give you a test over this. It's on the web, but you'll have to pick basically the bandwidth you want to use, and depending on your spectral resolution, we have a lot of options in terms of the channels. I would argue a little overkill. Very few people need to observe 23 megahertz with 500,000 channels, especially if you're dumping the data fast. That's a lot. You can produce a lot of data very quickly. That's a bit overkill for most astronomical purposes. There's 16 separate spectrometer channels. They're broken up into what we call banks, 8 banks. So we have 8 dual polarization banks, and we got they divided up between your different beams and different frequencies. If you have one beam, for example, in principle, you can throw the entire Vegas, and you can do sub-windowing, and you could have 8 banks, and each bank can be broken up into 8 separate windows. And you might have broke out. I just had a little thing that flashed up and said my internet was unstable. Now it looks to be okay. So anyway, the Vegas can be broken up into, and you can do you can observe a lot of different spectral lines at once. And the rules in terms of how you connect it up depend on receivers. We won't go into all those, but your friend and observatory staff can help you with that. The bottom line is, if the basic rule of thumb, if it's a single beam receiver, you can throw all 8 banks at it. If it's a dual beam receiver, typically you're limited to 4 banks per beam of your receiver, except for Ka, where you can actually use the full system. We have a special wideband mode. This is even probably completely unreadable, but this just shows there's a whole bunch of Pulsar modes too. Ryan and Andrew and Bren will be going over the Pulsar stuff with our Pulsar groups. So I won't go into all that. In terms of the GBT specs, this is again from the proposal guide. This is just to put it into the talk. I'm not going to go through this, but that's just sort of our basic specs. And Karen showed a plot similar to this in terms of showing the system temperature across their full observing band. We're missing some coverage in here. This is the band, the oxygen line at 60 gigahertz is in here. And then we go all the way up to, well, I need to update this. This is an old one. This only goes up to, I apologize. This is from an older talk. I should make it go all the way up to 115 because we go farther. So this was before we even had Argus and Mustang. So that's fully up there. So I will update that for next time. At lower frequency, you don't really have to worry too much about the atmosphere, but at higher frequency, you do. The atmosphere can come in and it can change a lot as a function of time. And so the thesis can vary quite a bit. So, but to get around that, we schedule higher frequency when the weather is good, and when the weather is not as good, we schedule low frequency where the science is not dependent on the weather. About 50, the site, even though we're in the east, our elevation isn't really that high, but actually about 50% of the time during our high frequency season, we have good water vapor, meaning we can actually observe at 3 millimeters. There's a memo on that. So this is just a histogram in terms of the precipitable water vapor. So we have a wet tail, but we have a lot of really good 5 millimeter water vapor. Here's sort of the mode of this distribution is actually quite good for 3 millimeter work. In fact, we used to do 1 millimeter work at Owens Valley when water vapor was like that. So when the weather's good here, like right now and last night, it was spectacular. It's very dry and it's very good. We're a big dish, so the winds actually can affect us. It's like a big sailboat, except it's not on water. And you don't want it's hard to observe, and you have large wind gusts. So this just shows, and it comes in not with the velocity squared, basically. And so your wind limit. So when we're observing up at 100 gigahertz, you want to have pretty low winds, or to have the dish stable enough to observe, which we have that about half the time. So we observe up to about 5 miles per hour. If it gets above 5 miles per hour, makes it very hard to observe at the higher frequency. The arm shakes around. There are ways to correct for that, and we're working on ways to improve that in the future. The telescope is scheduled through dynamically. We call it the DSS. If you ever hear the DSS, go into the DSS, they'll say, and put in your blackout dates or enable your sessions. That's the system in which projects are scheduled. One aspect of that system is the weather predictions. And so it tries to figure out what projects could be observed at any particular time based on weather availability, and also whether projects have been enabled, and also whether observers are available. So anyway, this enables us to take advantage of the good weather when we have it to do high frequency science. And there are about 450 hours, roughly, per semester, twice a year. And when you factor in all the constraints, opacity, winds, and also our NSF open skies times, since we're not all open skies anymore. And this just shows the aperture efficiency as a function of frequency, and we're still pretty good even at the higher frequency end at 0.3, but it does drop off. If this is an exponential curve, we wouldn't be good at 1 millimeter, for example. And although the telescope was commissioned in 2000, one could argue it was 2009 before it was fully ready to do high frequency work. This just shows a picture of the dish over that campaign in 2009 to improve it. I wasn't here at the time, but the people that were did an excellent job. This just shows pictures of the dish at the top and sort of the effective beam at the bottom. And here I did do this work in terms of looking back historically, and it was really impressive to see how things changed over time. So if you just, this plot here, concentrate on this plot here to the right, this shows the effective aperture efficiency over time as measured. So in 2003, when wasn't very, you couldn't really use high frequency. And then this is the work in 2009, at the beginning of 2009, at the end of 2009. But even then, they fixed the actuators, but they didn't have all the models in place to correct for when the dish turns over at a different elevation, you would have a huge drop off in efficiency. But over time, we improved those models and we flattened what we call the gain curve off till, and which you can see this is measured at 43 gigahertz, the same sort of numbers instead of the 80 gigahertz, and we flattened this off. And if you invert this around, this would be the one of the bottom right shows the effective surface errors as measured on the telescope. So we were, 500 micron errors. Now we're pushing down to 200 microns. That's about our fundamental limit. We're getting pretty flat. We might be able to push this curve down from 220 down, 210 to 200. We can't really go much below 200 unless we, because of the panel separations and the subreflector. That's sort of our fundamental limit. So we're approaching what we can physically do with this current telescope, but it's still impressive to see the generations of staff who worked on this and improved this over the last 20 years. So we can observe it all the way up to 116 gigahertz. This is the first, second light, but it was the first 12 CO spectrum ever taken with the GBT of Orion. And this is on a log scale. Karen showed you this to show the beam early on. And here just shows all across the Argus band in terms as a function of frequency. We're approaching, the beam size is about, 1.2 times lambda d, as we expect. And this is just, I'm not going to go into the calibration results. This is all in a calibration memo we wrote up a couple years ago. And it is quantifying our performance of our telescope, the aperture efficiency and measured main beam efficiency. This is with Jupiter. So you get, for extended objects, your efficiency is higher than on point sources because you're more sensitive to a larger beam. Anyway, and here are those parameters. It's all in the memo. I guess the one point I find it's truly unique about the telescope in a way, only maybe 1.5% of the light, if you look in the entire air and beam pattern of the telescope, sees the ground, so to speak, or sees the backwards direction. That means 98.5% sees the forward direction on the sky. And of that, a huge fraction of it, 96.5, we call it the forward spillover efficiencies. But anyway, if you multiply these two numbers, that would be in the air pattern. So roughly the fractional power within 1 degree of where you point is about 95%. You don't have that with regular telescopes. That typically the best you get is about 80%. And that's due to the fact that it's an unblocked aperture. And clear performance. So in terms of, let's just say you're going out on the sky and you say, okay, I want to point to some random spot for your telescope. Our blind pointing is roughly 10 arc seconds, which is nothing when you're doing L-band with a 9 arc minute beam. But if you have a 7 arc second beam, you can be off a little bit. So you need to point up at the higher frequencies. If you point on some part of the sky and you go to some other part of the sky, you could be roughly about 5 arc seconds off. So again, if you're doing high frequency work where your beams are small, you want to find a nearby object to do an offset pointing, and then your errors are of order only 1 arc second. In terms of the surface, without the active surface turn on, that means you're making dynamic corrections. And we do that for C-band and above. So Pulsar people, when they observe at L-band or prime focus, they don't really care about where the actuators are. They can just lock those in place and observe with almost a perfect mirror telescope. But at the higher frequencies, we use those actuators to adjust the surface. And if you don't do what we call these out of focus holography observation, that's what the OOF acronym there is about. And we use that to measure additional corrections on top of the gravity model. We call them the thermal corrections. So, and if you are observing during the day, your surface is about 0.35 millimeters. Without those corrections, at night, you're a bit better, about, maybe 0.3 millimeters. And then with the OOF corrections at night, you go from like a border of 0.3 millimeters down to 0.23 millimeters. And you might say, well, that's only a small change, but that's a huge change in terms of your efficiency. I should have put the Roos equation on there. It's like an exponential. It goes with an exponential, basically, in terms of your aperture efficiency. And our long-term goal is to push that down to about 0.2 millimeters or 200 microns. Observing strategies, okay, I have about 10 minutes or so left. I'm gonna leave some time for questions. So basically, I mean, your observing strategy depends on your science goals. I mean, if you're doing spectral line work, these are, obviously that's, which is different than if you're doing continuum work. So this just shows a picture of spectral line for neutral hydrogen or galaxy, and then there's carbon monoxide down below. Continuum work, you'd be doing different science as well. If you're studying free or thermal emission or synchrotron emission. Pulsars, you're studying variable work. Then you want to take high time resolution data. And we have a lot of observing options, thousands of them in principle. And basically, you pick your receiver, obviously based on the frequency that you want to observe at. You pick your back end based on what you're trying to do, line, continuum, or pulsar work. Your observing techniques are based on what you're trying to do in terms of your science goals. Are you studying a point source? Are you trying to map a large field? Are you looking at narrow spectral lines versus broad spectral lines? Each of those decision points lead you down a different path in terms of your observing strategy. And we'll work with you, and that's where your friend of the telescope can help you out. And then your calibration strategy also depends on the receiver that you're using, as well as your science needs. Basically, radio telescope different backgrounds. We measure what we call an antenna temperature, and that's basically over your atmosphere in the sky. So what we do is we do on-off observations because we make relative measurements, because typically your source is much smaller than all these other contributions. So, and then the name of the game is basically figuring out what's the best way to do this on-off observations for the type of science you're trying to do. We have frequency switching, where you're actually switching the LO rapidly. And we do use this for narrow bands. And then we have position switching, which is a more traditional thing where you actually can move the telescope, which we call that nodding, or even on-off. Nodding is that you move the telescope put the source into, if you have two beams, you put the source in one beam, and then you go and nod and put the source in the other beam. And then we have sub-beam nod, where you're not moving the whole telescope, you're just moving the subreflector to switch the source from one beam to the other using the subreflector. So in terms of position switching, here's just an example band pass. The source is right here. You really can't see it, but you do it on-off, then you can see the weaker signal in here. Frequency switching, as I said, is switching the LO. This is a diagram for an LO. So the idea here, you have that's what the sky looks like. Your bandpass, underlying bandpass looks like that. With one LO setting, the line's over here. With the other LO setting, the line's over there. You subtract those off, you remove the bandpass, and you get a nice flat. This is an idealized case here. That's not real data. And then you could basically, what we do is fold and shift and average that. And you'll see a signal like this, basically, where the minus signs are half power because you took an average, and then that's frequency switching. So to pick between frequency and position switching, if you're doing narrow lines in a non-crowded spectrum, so a lot of chemistry work, yes, kitty, you can go off, or maybe not. So if you're using narrow lines, you can do frequency switching if it's a non-crowded spectrum, meaning not a lot of lines. The people that are doing faint chemistry lines, it can be a lot of different signals, and if they're not sure exactly what they're looking at, you wouldn't want to be switching different lines into other lines. It confuses the spectrum. So a lot of the chemists will actually do frequency switching, even though their lines are narrow. So if it's a broad line, we recommend frequency position switching. And the definition of what these are loose definitions. There's not a hard and fast rule. A narrow line is less than 10 kilometers a second, broad line, more than 100 kilometers a second. So the advantages of frequency switching are always on source. If you're position switching on a big extended object, sometimes you have to move quite a ways away. And then you're only spending half the time on source. Now, observing modes, whether you're a small source or large source, if your source is, so this is sort of a flow chart in logic, if your source is smaller than the beam, you're using line observations, and you want to do position switching. There's multiple ways you can do position switching. You can, if you have more than one beam at a higher frequency nod, you can nod between two beams since your source is small. And if you're not limited by baselines. So sub-beam nod, you can move your sub-reflector faster than moving the telescope. And we use that for Ka, Q, and Argus. And we use nod for K-band and W-band because those beams are far apart on the sky. If you only have one beam, you can't nod or sub-beam nods. You just do traditional on-offs. You move the source in a beam and then go look at blank sky. That's it. These are actually observing commands: sub-beam nod, nod, on-off. Those are actual asteroid commands that command the telescope. You can also run a track command and put in offsets yourself. Instead of doing on-offs at lower frequencies, a lot of times what people would do, they'll do an off, on, off, on, off. You do more ons than offs just to spend more time on source. If your offs are not changing that much, which you can get away with low frequencies like at L band. Higher frequencies, you don't want to do that because the sky is changing so much that you want to take a lot more offs. So if the source size is smaller than the beam and you're using the frequency switching, the command you'll use is just, you can use a track command that just says track your source. If you're doing continuum observations, all this above was for line observation, and you're using a small source, I recommend doing a daisy map, which I'll show you here in a bit, what it looks like. You're just slewing over the source and making a flower pattern. So if that's for small source. For larger source, then it's a question, is the map larger than the field of view of your instrument? And if it is, then you could just do what we call an RA long map or a deck lap map, and you're literally going back and forth and painting in a picture. Now, if the map is actually smaller than the field of view of the instrument, that optimal method really depends on a lot of different factors in terms of how deep you want to go. You can still use RA and deck mapping, but the problem there is you have a lot of overhead. If you're a small, you have to slew off your source and come back, so that you spend a lot of wasted time on the edges around your map. You can do daisy maps if you're mostly interested in the central point or clump. We have these other things called box scans where you can move around within a box without, stopping the telescope, turning around and bringing it back. And then you could even do what we call like a grid map or a traditional point map if you really need a spectrum and you don't need too many points. You just sit and for whatever amount of time, and then you just take different spectrum. So this sort of shows you a layout of that. Like a point map, you literally just move the telescope to different points to fill in your grid. You're on the fly mapping. is this is what we do here, the RA long map, where you map here, and then you come back and map here, and come back and map here. And then we can also do the deck map, like here, here, and you're painting in the picture, or basket weaving. In terms of rule of thumb, you should Nyquist sample in the cross scan direction ideally. 3 times, here it says 3 time Nyquist sample. I even do 4 to 5 times Nyquist sampling along the direction of the slew, so you're not smearing the source out at all. Daisy mapping shows a layout here where you take these petals and it processes around basically to fill in your map. So you get really good coverage here in the middle of the map and less coverage on the outer part. So calibration, real quick. Basic calibration, we haven't, our definition of the antenna temperature is on minus off divided by off times the system temperature, and the scalar factor that scales your spectrum that defines your system temperature. It can be determined several different ways. Most receivers, we have noise diodes, which are great. This is just a schematic from our educational telescope. You can flicker a noise dial on it. We know something of known signal is here. We know how bright it is. So then when you observe something, you can scale to the noise dial. And all of our receivers have noise diodes except for W-band and Argus and Mustang, which do not, the 3 millimeter receivers. This is an example. You can have hot and cold loads, the same thing. If you observe a load in which you know its temperature, the difference between that and the measured counts that you see in your back end, you could use that to scale your data, to put it on a temperature scale. Now, to get those temperature scales on an absolute, those noise diodes as well as the hot and cold loads, to get an absolute measurement, we generally tie to the VLA because they're monitoring the calibration of some standard quasars very regularly. So from 1 to 50 gigahertz, well, even below, it even goes like whatever, a few hundred megahertz to 50 gigahertz. We use the GBT, the VLA calibrators. At higher frequencies, at 3 millimeter, in the past, I was leveraging the ALMA work because ALMA kept looking at the same sources on the skies at 3 millimeter a lot. So they calibrated those. ALMA's been down for the last year because of COVID. So we've been a little more creative in how we do our calibration. We've actually have to do it directly to Mars and go from Mars to our nearby, our quasar sources. In terms of observing practices, antenna optimization, low frequency, you don't really have to worry too much. The antenna is perfect effectively from my perspective, from an optics perspective, and an ability to point and focus in the surface. But at higher frequency, we have general rules at different frequencies. As you move to higher and higher frequencies, the C and X band, sorry, we use these radio terminology in these bands and radar bands. So this is moving to higher frequency. You have to point and focus more often. When you get in 3 millimeters, I would even argue you have to point and focus every 20 minutes. Maintain the pointing on your target. We have these corrections called auto-OOF that corrects the surface on top of our best models that we can use to set the surface based on gravity and conditions. So this corrects the surface for residual thermal effects. And we use this now at Q-band and W-band, that's at what they say above 40 gigahertz. W-band's at 3 millimeters. And the OOF solutions are typically good at night. If the things are relatively stable, you can do an OOF at midnight and it'll be good all the way until 6 a.m. The daytime, we typically don't do the OOF right now, and this is where we are hoping LASSI can help out because the surface is changing so quickly on time scales of 30 minutes to an hour. And I found that people are try to chase the surface solutions with their science. So the surface is changing so much. They do an auto OOF, they set the surface, but by the time the auto OOF is done, and they apply those corrections, the surface has changed, and it can actually do more harm than good during the day right now, because the auto takes too long to run, basically. So in that case, we actually run with just the default surface corrections that fix for gravity, because of the residuals around that, it fluctuate during the day. And that's all I had in terms of formal slides. So I'm going to get out of, whoops, I'm going to stop my share. And I probably have some questions.
I can ask them to you, Dave. There are a few that are further
Okay.
back. So thank you for your talk. The first question is, can the GBT be part of the Event Horizon telescope?
Not directly, because it works at 230 gigahertz, but that M87, that was that object they detected with the Event Horizon. So we go up to 3 millimeters at 150, 100 gigahertz, not 230 gigahertz.
Here's a question about a gamma ray burst. Will the GBT perform follow-up observations for the recent GRB from the furthest known galaxy? And is it possible to find its counterparts at radio wavelengths?
I don't know if we're going to follow up or not. I assume somebody will put in a proposal. They generally do, because to follow up these things. But in terms of locating the position on the sky, the GBT's beam is set by the observing frequency they look at. A lot of times they use the VLA to follow up objects. But we can get so it was found at whatever. So we can find it down to arc minute type positions, basically, with the GBT. But if you're trying to get down to the sub-arc minute, then you would want to use an interferometer.
Ryan also put a bit of an answer in for that. One thing about these new sort of fortuitous events, at any time during the year, you can put in a DDT proposal. If there's some big gamma ray burst and you want to follow it up, you can put one in, not just in the February and August proposal calls. So there's a limited amount of time for that, but it's for those sort of time-sensitive events. So another question is, can we use the Vegas continuum mode for low-frequency observations?
Yeah. Yeah. Use the DCR. So a lot of people you want to use the Vegas in continuum mode to remove, for example, you can narrow band RFI. It wasn't necessarily designed for continuum work, but it works. It works just fine for continuum work. In fact, Will's using it now.
Yep. So for position switching for dual beam observations, is there an amount of time
Mm-hmm.
where neither of the beams are on the source?
Yeah, when you have to, and yes, when you're moving the telescope from one beam to the other, then you do that between scans. So generally there's a 5 to 10 second overhead when you move the telescope. And then if you use the subreflector nodding, it takes about 1.5 seconds or so. It depends to move the subreflector, so that data is blanked, basically. So every time you move it for regular nod, you lose 5 to 10 seconds every cycle, and sub beam nodding, you lose 1.5 to 2 seconds.
Another question on nod, and I think this is the last one. On nod with 2 beams for position switching of small sources, how is it that it could be limited by baselines?
I'm sorry, I mangled what I was trying to say there. Basically, the baseline's nodding, you can, since you're moving the telescope, you can only typically nod, and we typically only nod every 30 seconds. So the faster you can move in position switching, the better your baselines can be. So if you move quicker, like with sub-beam nod, we can switch up 4.5 seconds is our maximum switching speed for sub-beam nodding. You're moving back and forth quicker than being able to move with the subreflector than moving with the nod. So, so depending on what people are doing, if you're doing extragalactic work where you have really broad lines, where the baseline wonkiness will affect your ability to make those measurements. And for KA, Q, and R. I guess I would use sub-beam knot to get better results, but for everything else, I would use knot with my, right.
All right, I think that is all of the questions. So thank you again, Dave.
Thank you. So, oh, I think I gave up the share.